It's time for something a little bit extra. And it's a little bit extra this month. Good afternoon, everybody, and welcome to another Geo-Institute live stream. It's GEOSTRATA Extra, and if you said to yourself, but they already did an episode from the February-March issue, you'd be correct. You can go back and watch that anytime you want on the GI YouTube channel. It was John McCartney and Marcelo Sanchez talking about nuclear waste and unsaturated soils. You want to check that out sometime. But today we've got something new and different and very cool for you. My name is Brad Keeler. I'm the director of the Geo-Institute, and we're thrilled to have you with us today. GEOSTRATA Extra, as we'll tell you more detail here in a little bit, is where we go behind our signature publication. GEOSTRATA comes out 6 times a year. GEOSTRATA Extra, we feature an article and go behind it with the authors for an extended interview. You might find out why they put the things they did in the article. You might find out why they didn't put things that they didn't put in the article. Double negative there, but that's okay. Or a million jillion other things. If you don't know anything about the Geo-Institute, after you watch this here interview today, head over to geoinstitute.org, and there you will find out many things about us. I already used the word gazillion. I guess you could find out a gazillion things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and I feel very strongly that you will, you should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Last thing today, before we begin with our interview, if you'd like to read this issue or any back issues of GeoStrata magazine, you can do it so easily. Head to readgeo.com. And when you get to that website, you will be greeted with the current issue of the magazine. You can flip through back issues. It's as easy as clicking on the issue library. You can go all the way back to 2017, I believe. There's so much information here. The links are live. You can click on them, and I would go to the current issue again. And that's the topic of today's presentation. As always, for GeoStrata Extra, we are joined by one of our esteemed editors, in this case, Ken Fishman. We have all Northerners this week, guys. What's going on? Ken is coming to us from Buffalo, New York. Our speakers today are going to be Majid, Ghayoomi, and Ali Farahani from University of New Hampshire. Ken's going to tell you more about himself, about them, about the article, and then we're going to go. Ken, are you ready?
I am. So today we are talking about an article that was published in our last issue of GeoStrata that focused on unsaturated soil mechanics. There were certainly a number of interesting articles in there, some related to pavements, some related to landslides, unsaturated tailings, but all of them involve the need actually to measure moisture contents and see how these vary over time, which is really the topic of today's presentation. And I think it's very interesting that our authors come from the University of New Hampshire in Durham, and they're talking about measurements of soil moisture and referring really to some earlier techniques that used to be more terrestrial based. We would take point measurements with one instrument placed at a particular location. And as far as I know, at least one of the first land-based instruments for measuring moisture content in soils was actually developed at the University of New Hampshire in Durham. It was the guy with the last name of Campbell. He later started a company, Campbell Scientific. I think he's divested from that since then. But his PhD dissertation was actually about how to measure soil moisture by monitoring capacitance. And he developed a sensor that does that and measures salt content and temperature as well. So really, these guys are coming full circle and looking at how to expand this. So before we get too far into it, I'd like to ask Majid if he could give us just a little bit of a summary of the article that was published and tell us where we're going to be headed with this discussion today.
Yeah, thank you, Ken. And good morning, good afternoon, wherever you are. And I'm Majid Ghayoomi from University of New Hampshire, and joining with my colleague Ali Farahani, we are talking about this article that published. And the goal was to talk about the use of satellite data to get some information about soil moisture. If I allow, I can share screen, so I can basically go there. Okay, is it good?
Looks great.
So basically, the article is written in a way that we transition from unsaturated soil mechanics to soil moisture measurement. So then we talked about how traditionally we use point measurement lab data to get some information about soil moisture. And then now remote sensing came to help us basically to get some information beyond the point, and we can have a continuous measurement of the soil moisture over time. And that could completely revolutionize how we look at the events, especially geohazard event, and how the soil moisture changes during that event. And specifically, there are different satellites that people use, and specifically in this article, we put our focus on a mission called SMAP. We'll talk about it a little bit, which the main purpose of the mission was to measure the soil moisture. And then in the paper, we talked about two applications, one being use of SMAP for soil liquefaction, and also a little bit on landslide. And then we gave ideas of how this SMAP satellite data is being used in other applications. Just a quick note, if you are not familiar with SMAP, basically it was launched in 2015, and the main goal was to actually measure the soil moisture and monitor the freeze thaw and track the climate events. But the soil moisture was a big part of it. Originally, it had two sensors, a L-band microwave radar and radiometer. The radar one, which was, you can see the name say SMAP, is soil moisture active passive. So the active was a little bit higher resolution especially, but it failed 6 months after launch. But the radiometer, which is a passive one, it has been it's been sending the soil moisture data to us basically throughout the year. It has a very high temporal resolution. It's basically every 2-3 days visit any point on the Earth. The spatial resolution, the radar one was a little bit higher, but the radiometer one is a bit coarser, it's about 36 kilometers. But after the failure of the radar, they kind of configured it, and now the resolution is 9 kilometers. One last thing is that it's a very well calibrated satellite data. If you are interested, you can always go and look into the data. There are some other side products being generated, but for example, this is one data from a watershed in Oklahoma, and the dots versus the orange line shows the point measurement versus the satellite data. It's very well calibrated, and the performance is a little bit different depending on the cover of the Earth in that region. Just wanted to make sure that you have a little bit of background, initial knowledge about this map.
Thank you, Majid. You know, there's been such an explosion in the technology and launching of satellites over the decades. I mean, I remember 1962, they launched a Telstar satellite, and actually there was a tracking station not far from where I grew up in Maine. It was in Andover, Maine. This was a great advancement. It was the first time they could do a transatlantic television broadcast, and it used a microwave technology. And since then, there's been thousands and thousands of satellites that have been launched, and the technology has improved dramatically. So, Ali, could you give us a little bit of insight into some of the technological advances in Earth observation satellites, and a little bit more about microwaves and radio waves and how this is so useful compared to other emitted energy sources, and how this all kind of fits together to give us data that's of use in geotechnical engineering and other fields?
Yeah, hello everyone. I'm happy to be here with you to share some materials about our article and research. So let's start from the state of the art in soil moisture measurement. So for soil moisture measurement, we have basically in situ and remote sensing method. In situ methods provide so highly accurate and direct soil moisture measurement at a specific location. These methods include, for example, gravimetric methods, which is the gold standard that measures soil moisture by weighing and drying soil sample, and also different types of sensor that, like dielectric-based sensors that estimate moisture by measuring changes in soil's properties. And while these in situ methods are precise and still are the reference for soil moisture estimation, and there are big networks of in situ measurements in the US and other regions in the world, they are so limited in coverage and also expensive and labor intensive. So, and we have then remote sensing techniques that use satellite and other remote sensing platform to measure soil moisture at regional to global scales. So we have, for example, microwave radiometers like SMAP and SMOs that have been specifically designed for soil moisture measurement. And we have other platforms that their data can be processed and used for soil moisture estimation. For example, we have microwave radars like Sentinel-1 or optical and thermal sensors like Landsat. And also we have LiDAR that primarily used for terrain mapping, but contributes to soil moisture studies as well. So remote sensing provides large-scale coverage and frequent updates, but resolution and accuracy can be affected by different parameters like vegetation, terrain, and sensor limitations. So the vast network of NASA's Earth observing satellites covering a wide range of environmental and climate monitoring application that we can see in this slide. So these satellites fall into different categories, including weather, land, ocean, and hydrology observations. For example, we have GPM satellite launched in 2014 that measured precipitation in global scale, or we have SMAP for soil moisture measurement. Also, we have Landslide for a long time that provide imaging of land surface changes. So if we categorize these remote sensing platform based on energy sources in the next slide, we have passive sensors and active sensors. In passive sensors like optical sensors and radiometers, we depend on external natural sources of energy. For example, optical sensors like Landsat or Sentinel-2 use sunlight to capture images from the Earth's surface, while radiometers like SMAP or SMOs detect naturally emitted microwave radiation from the Earth. And active sensors like LiDAR and radar generates their own energy or signal and send that signal to the Earth's surface and measures the reflected signals. And another way to categorize remote sensing platforms is based on their wavelengths. So regardless of the source of the energy that we talked about, the energy that each platform receive and process have a wavelength and frequency. So the electromagnetic spectrum is the range of all types of radiation from high energy waves like ultraviolet in the left side to low energy waves like radio waves. So remote sensing instruments use different parts of this spectrum depending on their purpose. For example, starting with ultraviolet at the left, which has the shortest wavelengths used in remote sensing, which is a sensor, sensors like ozone monitoring instrument is used to detect ozone levels in the atmosphere. Then we have the visible range. We have sensors like Landsat and Sentinel-2, which capture reflected sunlight to study land cover and gives images from Earth's surface. Beyond the visible light is the infrared range that Sentinel-2 and MODIS satellite use this band. And then we have the microwave range, which is crucial for soil moisture sensing, where SMAP, SMOS, and AMSRE satellites detect natural microwave emissions, while Sentinel-1 radar, which is still in microwave band, actively sends and receives a microwave to map Earth's surface. So, but there's a question that why microwave remote sensing is more suitable for, soil moisture measurements. Microwave remote sensing can operate in all weather and lighting condition, which making it reliable for continuous monitoring. I mean, unlike the optical sensors that because of having lower wavelengths, they cannot penetrate cloud and low to and vegetated areas. Microwave remote sensing allowing us to measure the Earth's surface even under, for example, cloudy sky or in regions from low to moderate vegetation. And several factors influence how microwave radiometers and radars detect soil moisture. The most important factor is the water content, because water has a high dielectric constant that strongly affects microwave emissions. And that is one of the most important reason that we use microwave remote sensing for detecting soil moisture. And when the wet soil absorbs, for example, more radiation and sends less signal to the satellites, and while dry soil sends more radiation to the satellites. And also surface roughness also plays a role, because rougher surfaces scatter microwave signals, which can alter both radiometer and radar signals, making soil moisture estimation more complex. Or vegetation also attenuates and scatters microwave signals. However, the L-band microwaves, which SMAP, like those used in SMAP, can partially penetrate moderate vegetation layers, which is an advantage of using SMAP for soil moisture detection.
Thank you, Ali. That was very interesting. Majid, I was just curious, how did you get started in a topic like this? Are you a space geek, a soils geek, a physics geek, all three? What got you started in this, and what's the background?
I guess we all like space, right? But from the traditional work that I have been doing research in unsaturated soil for a long time, and basically trying to understand the geotechnical properties of the soil under different moisture conditions. And specifically, my research has focused a lot in the last 10, 15 years on the seismic response of unsaturated soil. So the unsaturated soil mechanics is pretty complex because you have a lot of players, the precipitation, water flow, water table, evaporation, all of that will impact the moisture profile in the soil layer. But when you talk about the seismic events, when the earthquake happens at the bedrock, it propagates up to the soil surface. Of course, it goes to the foundation. There are different aspects of soil structure interaction involved, the performance of the structure and the settlement of the soil layer and the foundation. So all of that will be impacted by the soil properties, specifically the moisture content. And that has been the issue that I have been investigating in the last decade or so. So for example, if we have this system, now if the water table changes, how will impact the seismic response of this foundation or this structure? So over the years, we investigated different aspects of the seismic response of unsaturated soils. For example, a couple of things that I want to note. For example, we did a lot of cyclic direct simple shear tests to investigate the effect of degree of saturation on seismic compression. And obviously, when the soil is fully saturated or dry, the response is different when you are in the middle degree of saturation. And you can see the settlement or the seismic compression goes to a optimum value, lowest value in the middle range degree of saturation. And of course, we investigated, for example, the effect of fines content. So overall, we can see the compression will be impacted by degree of saturation. So that means that soil moisture will play a role there. Or for example, if in another set of research, we looked at the pore water pressure generation of unsaturated soil, especially on the nearly saturated soil. That's important when we look at the liquefaction and some of the techniques that people have developed, and we have also worked on the induced partial saturation for liquefaction mitigation. Basically, as you drop the degree of saturation, the pore water pressure generation significantly drops. So that's also another aspect when we talk about earthquake impact on soils and buildings. Compression, for example, the pore water pressure, those are the things that are important to us. And those are the parameters that all directly get impacted by degree of saturation. For example, we also did a lot of different centrifuge tests. Centrifuge testing is one of my hobbies, not hobbies, my research toys that I do a lot. And we looked at what will happen, for example, if you apply earthquake motion in the soil layer when you have a structure on it, and then the water table drops, right? So some of the results are intuitive, but it's good to see the effect and quantify the values. So for example, in this example, if I plot the settlement, these deltas for the free field versus the structural or the foundation settlement versus the degree, the level of the water table. So the DW stands for the water table. So as the water table goes down, obviously the soil gets desaturated and the settlement decrease, both in terms of the free field being the triangles and the structure, which is the pluses. So that would be intuitively, people will say, yes, the water table goes down, soil gets stiffer, and basically the stiffer soil would have a lower settlement, right? So these are from the mechanistic perspective, and then some tests we did in the lab, measurements in the lab, and I know some other people did a field monitoring, but these are very point-based data. So the idea was, okay, let's take it to the system level, right? And then when we talk about system level, there are three aspects of it. We have the seismicity, the earthquake, the motion, the peak ground acceleration, the spectral acceleration, the frequency content, the geotechnical properties, right? Where soil moisture being one aspect that we wanted to focus, and that's the key to this study. And of course, the resiliency, then the response and the overall impact. There are so many different aspects of a disaster that goes to the resiliency, it's not just the technical part. But if we just take this middle part, the geotechnical properties, and take the soil moisture, what we have been doing is that we have been trying to relate the soil moisture to earthquake impacts, right? And we have been using the lab and numerical modeling. So the goal was that to understand how the soil moisture changes during earthquake. That's one question. One other question is, what would be the impact of the so-called pre-quake soil moisture on the site response, on the damages to the buildings and the structure? So we have been doing this in the lab using centrifuge modeling. And then I was in a presentation and I learned about SMAP, and I saw, oh, that's very interesting, because this can take our work to a bigger scale, like different level. So we try to move from the lab and computer to basically remote sensing. So basically remote sensing plays this bridge between the soil moisture and earthquake impact. And that's where basically the idea came about. And then for that, we decided to use SMAP. Of course, there are other satellites that Ali explain, but we specifically pick SMAP because we are part of that SMAP science team that we are looking at different application of SMAP satellite. So one just before close the answer to this question, the first thing we decided to do just check the evidence of really this moisture change occurs before and after earthquake. So for example, imagine if you have a target earthquake and you have an area coverage and your grids show the data coming from these are each 9 kilometer by 9 kilometer coming from the satellite, and we get the data from SMAP pre-event and post-event, and basically try to see can we capture any moisture change. And this is one early plots that we develop. For example, on the left column shows SMAP, the soil moisture change before and after. If you take the the soil moisture after the earthquake and subtract the before earthquake from it for each grid, that shows the soil moisture change based on SMAP data. And for 3 different earthquakes, this says Greece earthquake, Italy earthquake, and Taiwan earthquake. And that very right plot shows the precipitation. So the red means that there was no precipitation whatsoever before. So one may say, oh, how you can prove that's because of earthquake that the soil moisture changed, right? That's always a question people ask, but we need to check that. So no precipitation. There is another model-based soil moisture estimation provided by NASA. I will discuss it if it comes to that question, but that shows that without continuous high temporal resolution SMAP data, we couldn't capture these blue points, which are the soil moisture change right before and right after earthquake. So that was a good evidence that, okay, with SMAP, we are able to capture the earthquake impact. Remember that the earthquake impact, if the temporal resolution was not high, the soil moisture change will be gone in a week or two. We may, the water will recede, we may not see it. So the temporal resolution becomes very important. So that was the evidence. So we wanted to go from that lab-based modeling to a little bit of higher spatial scale and understand the earthquake impact. That was the main goal where we started this project.
Thank you. Well, with that as a background, let's dive a little deeper into some of the data that you were showing in the paper. How does the satellite data help to uncover soil moisture changes before and after events?
Okay, yeah, that's good, great point. So, for example, this was the evidence. This showed that okay, there is a promise. So for that, we went in and actually we relied on the reconnaissance effort, because you know that there's a GEAR, for example, geotechnical earthquake engineering reconnaissance team. There's a STEER for structural, and there are other ones. And also sometimes the locals report. So we need to make sure when we say, okay, there is a high moisture change in these points, what happened? And then we can find the location and see, oh, there was a liquefaction in that area. So what we did, so if we go back to SMAP, SMAP has a core product that's the soil moisture, and as Ali was talking and I mentioned, is a resolution and there's a temporal resolution, but also there are other products. One is called pre-event root zone soil moisture, which goes a little bit deeper from the 5 centimeter original SMAP measurement, but also it has other higher resolution that combine the SMAP, for example, with Sentinel. So that aside, so we define 2 type of data. We use 2 type of data from SMAP. One is basically soil moisture change. That means if you have an earthquake, the day before earthquake and the day after, right? It's 2-3 days temporal resolution. So we subtract one from other, that gives a change of soil moisture just because of earthquake. That's one aspect. Remember 2 hypotheses we had. One was what happens during earthquake, how much moisture change. The other one was the impact of the initial soil moisture. So we developed this pre-event root zone soil moisture. That's the soil moisture right before the earthquake, right? So these are the 2 parameters or 2 maps we want. As I mentioned, when we started this, when I talked to someone, the first thing was that, oh, how do you know that maybe this time of the year the moisture should go up naturally, right? It's just it's a hydrologic process. There might be water moving from the mountains to the area. So that is a good, correct question. So NASA has a program called GLDAS, which is the Global Land Data Assimilation System. Basically, they have a lot of different models, right, combined together to predict the soil moisture over the year for each location. And that also sometimes use the satellite data, empirical data, field data, and it's very robust, very well calibrated, long time being there. So we said, okay, we have the soil moisture data variation from the satellite, and then we also have the GLDAS data, which doesn't include the temporary or momentary impact of the earthquake. So if we compare these two, we should be able to get some information about what will happen during earthquake. So that's what we did. We developed this protocol. So we have the pre-event and post-event soil moisture, get the moisture change based on the SMAP. Also, we have the GLDAS soil moisture change in the 2 days that we are looking at. So if we subtract the moisture change from the SMAP and the moisture change from the GLDAS, basically that will tell us the moisture change only because of the earthquake, right? Because the natural changes of moisture is embedded in GLDAS. And that's how we develop this parameter called moisture difference index that really tell us the moisture change just as a result of earthquake. And that was really helpful because we eliminated that uncertainty where, for example, what about the impact of precipitation or natural changes to the ground that will change the moisture? Okay, so that's how we basically started this, and then we developed this moisture difference index. So, for example, this plot is one of the plots that we presented. It shows the ratio of grids. When I say grids, means those little pixels, right? With positive MDI. Positive MDI means that the soil moisture increased, okay? As a function of peak ground acceleration on vertical axis and the shear wave velocity, okay? So shear wave velocity shows the stiffness or maybe the density, right? Denser soil is stiffer, higher shear wave velocity. So if we look at it, look at these points where the lowest shear wave velocity, that means looser soil, and higher intensity earthquake, higher PGA. We have the highest ratio of MDI positive, which intuitively makes sense, right? So you have a stronger earthquake, you have lower shear wave velocity, that soil is more susceptible to change. If there's a compression, right? For example, compression will increase the moisture content because you are getting rid of some of the voids, and the more of the voids is with water. So that shows that, okay, with this, now we have a measure of the change of soil moisture just because of the impact of the seismic event. So we take that, now we know that we are able to eliminate the natural processes and everything, and we can isolate the impact of earthquake. So we did that, and we looked at many earthquakes, and we also used whatever data available to us. As I said, we went to all the gear and steer reconnaissance report. We read local, for example, this is an earthquake in Indonesia. They had their own local report, like what are the people go in the reconnaissance teams, they'll take pictures. So we try to identify those and put them on one map and see wherever we have these blues, which are the higher change of soil moisture, are those the areas that really impacted from the ground truth data. And that showed that really we are able to capture those. Of course, there are limitations. One of them, of course, is the spatial resolution, but that's a very big step because now with the satellite data, we can figure out where are the areas that we have a high moisture change in future that could be used for immediate response actions. Because if you just, for example, if a large area got hit by earthquake and you want to know where to go first, you have an idea where are the areas you have higher moisture changes.
Thank you, Majid. That was very clear. You make it look easy, but let's dive a little deeper into this. And Ali, can you tell us how SMAP can specifically help with geotechnical engineering applications? For example, how it might be applied, specifically for liquefaction assessment.
Yeah, so as Dr. Ghayoomi says, because soil moisture is an important factor in many geotechnical problems, SMAP can be used as a tool that gives us the actual and near real-time soil moisture conditions on Earth's surface. For example, we have done studies for soil liquefaction as well as landslide by involving SMAP data. Here I want to talk about contribution of SMAP in soil liquefaction model. For this purpose, we collected a liquefaction database including both liquefied and non-liquefied points for 11 recent earthquakes, and there were promising results. For example, if in the next slide, we plot a heat map for observed percentage of liquefaction probability, I mean the share of liquefaction cases as a function of pre-event root zone soil moisture and moisture difference index, we can see that the share of liquefaction cases is pretty much higher in cases with more wet condition. So from the literature in the next slide, we can see that there are three different groups of variables involving in liquefaction models, which are site conditions like shear wave velocity, surface soil roughness, or seismic loading like the magnitude, PGV, PGA, and soil saturation condition. For the soil saturation group, previous studies in this field commonly used some proxies like mean annual pattern of water table depths or historical precipitation data, but these proxies cannot show seasonal variability and the actual soil moisture condition when the earthquake happens. So also some studies shows the result that in regions with high precipitation result in overestimation in estimate the liquefaction probability. So we try to replace the soil saturation proxies with the SMAP-based parameters like pre-event root zone soil moisture, the average surface soil moisture in 1 year prior to the event, and also the fine fraction that we get from the SMAP. So in the next slide, we have liquefaction hazard maps for 2 earthquakes. Overall, figure A in each earthquake shows that the current version of USGS global liquefaction model tends to show high liquefaction potential in the vicinity of all water bodies, regardless of the actual saturation conditions of the region. For example, for Haiti 2021, the current USGS liquefaction model flagged many regions in near to water bodies like rivers by red color. I mean the high liquefaction probability. Consequently, it overestimates liquefaction likelihood in such areas and misses liquefaction cases far from water bodies, and this could mislead earthquake reconnaissance teams. On the other hand, in figure B, that shows the SMAP-based liquefaction models, coarse resolution of SMAP obviously is the main factor that needs to be improved in the future. Studies, because of the low resolution of SMAP-based variables, it may not be able to narrow the region with higher liquefaction probability as the previous models. For instance, for Ridgecrest in 2019, SMAP model shows wider areas with liquefaction probability higher than 0.3 compared to the other model. However, this limitation can be modified as next generation of microwave Earth observing satellite with higher resolution like NISAR will be launched pretty soon, I guess, in the future.
Thank you, Ali. That was some very good technical content. But getting into some more practical discussion, Majid, besides this research, is this topic going to, or is it making its way into engineering education programs, either undergraduate or graduate courses? Do you introduce this in any of your classes? And what kind of background does a student need to start to learn about this and advance in this field?
Yeah, so I think we can actually, as someone who is passionate about unsaturated soil, let's divide this into two sections, right? Let's say we are talking about the remote sensing part and the unsaturated soil part. I think the remote sensing part is already got its way into our programs. Like, for example, in our undergraduate program, we offer courses in GIS, and they get to know a little bit about remote sensing data. And then student can go to a little bit of take senior elective and, maybe a little bit of, graduate school, master's student. There are courses in remote sensing we offer. So I think remote sensing already found its way. And then, most of the students and people are interested in this area. They take courses. They are interested to take courses. And also from the practical point of view, there has been a lot of work in the last 10 years, I would say, on the use of different remote sensing tools for different applications, right? For example, landslide, damages, the basically making 3D images of the objects on the ground, all of that. So there are lots of, application. I think remote sensing is already penetrated into our program and practice and find its way. And from the unsaturated soil perspective, it's like everybody knows that unsaturated soil is important and the behavior is different, but really, it's rarely we have, at least in the undergraduate program, we talk about unsaturated soil. Actually, this is something in international communities often we discuss in our committee meetings when we have international conferences, that how to bring the concept of unsaturated soil from just being a phase diagram kind of knowledge that, this is degree of saturation, that's moisture content of measure, into our undergraduate program. And I think now because we are way ahead of in practice in education, basically we need to make sure that we talk about unsaturated soil in a more mechanistic way, because there are different aspects of unsaturated soil mechanics. There are like hydraulic properties, thermal properties of the soil. All of that are impacted by unsaturated soil. I think we need to do a little bit of better job in incorporating unsaturated soil mechanics and hydraulics into our undergraduate and graduate programs, not in the sense of just introducing the fact that there is unsaturated soil, but also really how that will be getting impact, how that impacts the soil properties, right? So I think after that, because now people have a sense of remote sensing and how they have a better sense of how the unsaturated soil will impact the soil response, then these two marry, and then we have a robust base. Otherwise, if we don't convince people that unsaturated soil really impact the geotechnical response beyond the soil moisture content, beyond the phase diagram thing, really, if you introduce the best tool in the world, people are not using it because they don't see the value of using the tool for that specific application. So I personally think we need to do a better job in unsaturated soil education. I think remote sensing, because it's a little bit beyond our field, beyond geotechnical engineering, there are people who are developing instruments, really working on different sensors, all of that are already evolving and people are working, and we are adapters, right? We use those tools. So I think that is already in our basically profession. It's just we need to make the connection between the two fields.
Thank you. Finally, Ali, as someone who's been studying this and looking more into the future as you're kind of completing your studies and seeing how this can get applied and kind of entering the profession, so to speak. What do you think are the biggest challenges facing the use of satellite data and imagery in the geo professions? You know, in terms of the limitations of the satellite data, and I guess finally, I don't know if you can answer this, but if you could access any type of satellite and launch your own, what would you do with your satellite? What instruments would you use?
So, you know, while SMAP has been a groundbreaking mission for soil moisture monitoring, it does have some limitations and challenges that researchers are continuously working to overcome. For example, one major, as we mentioned, one major setback was the radar failure in 2015, which significantly reduced SMAP's resolution, leaving us to rely solely on radiometer data. Another challenge is the performance variability of remote sensing data. For example, SMAP's accuracy can be affected by vegetation cover, soil texture, and climate conditions. So we expect that we may not have good quality of soil moisture data for some regions, like for example, some regions in Africa, or for Amazon forest in Brazil or something like that. So because it cannot penetrate dense forest. Another key limitation is also the lack of sufficient ground calibration and validation in some regions, which impacts data reliability. So to address this, again, there is a big CalVal researchers are expanding calibration networks and integrating SMAP data with other sensors in the world. And despite these challenges, the future of SMAP and soil moisture research is really promising by integrating SMAP data with high resolution missions like Sentinel-1, that the SMAP team already did that and reduced and improved the spatial resolution from 9 kilometer to 1 kilometer, which is very huge. And also we have other satellite focusedly work on soil moisture called NISAR, that we can achieve better spatial accuracy to 100 meters, something like that, which I believe that will be a revolution for using soil moisture in geotechnical problems. And also advancement in AI and machine learning are also playing a crucial role in refining soil moisture estimations and making remote sensing even more reliable for geotechnical and environmental application, I think.
Thank you, and certainly thanks for all the presentations, the slides, and the information. But before we go in and look at some of the questions we might get from the participants, I'll give you a chance to make a few closing comments, Majid. In terms of what you think maybe the greatest prospects are, things maybe Ali might have already covered some of this, the greatest prospects for using the satellite and imagery, what you think the prospects for refining the resolution is, and creative ways that these techniques might be used in geotechnical problems.
Yeah, thank you. So I think as geotechs, we always, one thing that we, regardless of what area of geotech we work on, we're looking for, like, basically say case histories or like monitoring, field monitoring, instrumentation. That's something that, we have been doing for a long time as a profession, right? And as Ali mentioned earlier, that, instrumentation and, monitoring the field, we are not going to be completely independent of those in future. We always need those because those are our ground truth. We need those. But we know that sometimes they are expensive, very hard to implement, and some areas are not accessible. So we need to embrace the remote sensing and basically mix the two. So we cannot say we only rely on remote sensing or we only rely on field data. So that gives us room as a profession to grow and to mix the two and come up with new ideas, right? We can have a continuous data collection without if we want it or not, we have a continuous data collection and it's there. So we just need to take the data and analyze it, and we can apply it to whatever application we want. We want to be creative. Like, for example, I went and this SMAP community, they have their own meeting annually, and I attended some of their meetings. It's called SMAP Science Team, and almost everybody in those teams are either hydrologist or electrical engineer or weather experts, freestyle expert. So very much at a couple of meetings that I attended, there was no geotech, right? Although we are dealing with soil, so we should have some presence. So I think we need to be more active, and maybe in the future missions, we can have a say in the type of measurement, right? If we are getting involved, like when I presented, the community actually was very welcoming and said, oh, it's a new application. They were all excited on the seismic and everything. But I think we need to be involved, and we basically provide input when the new missions go up. So I think that is very important. And in future, there will be more satellite, as Ali said, higher temporal spatial resolution. If we have the framework ready and we have it streamlined, when the new technology come with higher resolution, higher, even there might be other sensors, like not just the moisture, other sensors that measure other parameters of the soil, we can immediately implement it in our practice. So I think the applications are there. We just need to embrace it and try to be a little bit creative on applying those. And I see a lot of people are doing that even in our geotech community. There are lots of people doing very interesting works, and I think it will grow in future.
Thank you. Actually, I just opened my chat, so I see I've been remiss that I should have been reminding everyone that they can put their questions into chat, but we did get a few. So either Majid or Ali can take this one, but one question is, do you think that soil moisture is more important for assessment of landslides than for liquefaction? Is it more useful for one than the other, or do you think it has value that equally applies to both? And do you find more benefits for actually looking at landslide hazards as opposed to liquefaction?
I would say they have their own role in each of these two hazards, right? So liquefaction, obviously, there is a water pressure, there is a water in soil, so that plays a role. If the soil is, so practically, if the soil is not fully saturated or nearly saturated, you wouldn't have liquefaction. So that means the degree of saturation is important. On the other hand, landslides, a lot of landslides are seismically triggered. Some of them are precipitation triggered. So regardless, the soil moisture, even if you don't talk about the seismic landslide, just regular landslide, which for the regular landslide, this SMAP has been already implemented, and people have done work, but less on the seismic landslide. But regardless, the water is in there. So knowing the soil moisture before the event. So this is the challenge. So always we have used soil moisture in the analysis we have been doing for a long time, right? But often we relied on data either from another location or predicted data or some data from the time of construction. So, but the remote sensing will give us the opportunity to know the soil moisture right before the event, which is uniquely put us in a position to have a better prediction of the response.
Yeah, thank you. I'm not sure I understand this next question, but I'm going to try. I think what this question is asking is he's asking what's the resolution of SMAP data in terms of penetration depth, and then I think he's trying to ask how do you divide or obtain the difference between where you're measuring the moisture in the top 5 inches and the root moisture measurement that goes down to I think a meter or 3 feet or so. Is how are those distinguished in the data?
So the penetration depths of SMAP data is surface of theirs is the top 5 centimeter of theirs for both fine fraction and soil moisture. And as we said, the surface roughness of the Earth affect the signals that SMAP or any other satellite receive, and by analyzing those signals, they can, there are some algorithms and equations to estimate the fine fraction, surface fine fraction of theirs. And yes, for both of those, the SMAP data is for the Earth surface, I mean the top 5 centimeters, but they also combine the SMAP soil moisture data with some models to estimate the soil moisture for the first 1 meter top of the soil, and which is the level 4 of SMAP data that we called it root zone soil moisture. And that data product is, very well calibrated, and lots of researchers used it for, different hydrology studies and also studies related to rainfall landslide.
Can you detect changes in soil moisture with depth? Is there any possibility for using SMAP data to analyze soil layering?
There are some studies that correlate the surface soil moisture with the deeper soil columns. So there is some correlation with the, for example, surface soil moisture with water table depths, or surface soil moisture with the soil moisture in deeper layer of the soil. But technically, for now, the most reliable depths that we can use, directly satellite-based soil moisture is the surface one.
Thanks. Those are the last of the questions that we got, and I think it's getting to the end of the presentation. I'm going to invite Brad to come back. I think he probably has a few parting words, and thanks for everyone for listening, and I thank you guys for a great presentation and really providing a lot of good detail about what went into your article, and just things that at least I didn't know, about what we can do with all these satellite data in different applications.
Thank you.
Thank you.
So, and before we go, I actually want to ask you guys a question. I mean, we don't have a lot of people in our community that are funded by NASA. Can you talk quickly about the NASA grants process? How is it different from NSF? And, what have you noticed as you've gone through it as a NASA grantee?
Yeah, it's a completely different community. And so actually I got to know when I started my career, I said, okay, NASA, right? It's a geotech. Let's get funding from NASA, right? Like you always have NSF, DOT, FHWA, and all of that, but it should be cool to get funding from NASA. So I had this idea. I was in a meeting. I learned about this SMAP, and I thought, okay, this is right into my work of soil moisture, and I have this idea. It's cool, and I'm sure they will buy it. So I submitted a proposal. There was a program called early, at the time I was like a new faculty, it was like early faculty something. So I submitted, it's like equivalent of career award for, NSF. So I submitted to that program, but because I didn't have any remote, satellite background, so the main criticism was like, the idea is great, but you don't have any basically background in the area. So I spent a couple of years building that background. And then I submitted, that was the time that SMAP, for example, has a science team program. So there is a program that is just for launch and maintaining on the orbit and everything. There is a group of scientists called science team. Basically, they are the applications, like NASA fund, because for them, there should be convincing that they basically keep the satellite in orbit. It costs, right? So every 5 years, the science team leadership submit a proposal to convince NASA to pay for the maintenance of the satellite. So, for example, if they cannot convince, that's done, that will orbit forever and no data will come back. So every 5 years, there is a call, for example, for this one. And that was about 2 years after my initial thought submitting to that early career program. And I say, okay, now it is the time because it's SMAP, it's a science thing, and I have a new idea of application. So I submitted. But in order to also basically strengthen my remote sensing, I collaborated with a faculty who had experience in this area, and she got, previous NASA funding, and so kind of helped me to get into their language. So talk to their language, because it's important to talk the language of people who kind of use this. So I submitted the proposal, and the result was very promising. And actually, whenever I presented the community, the SMAP community, they welcomed and they were excited about the new application, the seismic application that we come up with. And actually, I think last year there was they submitted a new proposal for continuation of the mission, and they need to submit there are several things that they need the science team leadership to submit, saying, okay, we check mark this application, this app. There was one part that was empty, and with our project, they were able to put that box checked as well. So they were also happy, so they could have a better presentation to NASA. But I think it's important to know the opportunities. There are lots of opportunities now that I kind of get involved in it. There are lots of opportunities that I think at Geotech as a profession we can contribute, but not a lot of time we don't get information about okay, there's this call or that call. That's one thing. And the other thing is that we are not really trained on the technical remote sensing part, and that as a profession, we need to build up ourselves a little bit better.
That was a great answer. And if you've got another second, we just had one last question come.
Yes.
And I don't know that you're going to be able to help this, but we're going to give it a shot. Currently, which mission or satellite provides the best available spatial resolution? Soil moisture data.
Oh, so for soil moisture data, the best reliable and SMAP gives us the best reliable soil moisture data in from 9 kilometer to 1 kilometer resolution. The 9 kilometer resolution is just solely based on SMAP radiometer, but the 1 kilometer resolution is based on Sentinel combination of SMAP data and Sentinel-1. And the thing is that there are more satellite with very higher resolution than SMAP, like in for example, Landsat or Sentinel 2 or 1 have a spatial resolution of something like around 30 meters or something like that. But the point is that their accuracy in capture the soil moisture is pretty low because of the wavelengths that SMAP is operating. That helps SMAP to get the best accuracy for detecting soil moisture. And that's the reason why we did not get higher resolution so far. But hopefully with NISAR, we can, improve it to 100 meters or less than that.
That was great. Fantastic. So we got a little bonus answer there. I appreciate it, Ali. So Ali, Majid, you guys did a great job. This is a fantastic presentation. I love it because space, that's where I came. Well, not literally, but that's the field that I came from before I came to ASCE. So it's nice to get a little taste of that every now and then. And Ken, great job doing the interview as always. For our viewers out there, if you liked what you saw today, and you probably did because you're here at the end, again, click like, subscribe, and get notifications, and we will lovingly let you know every time we post something to the YouTube channel. Next live stream is a week from today. It's March 25th, next Tuesday, and it's going to be the GI annual business meeting. So you want to hear about what's happening at the Institute, across the society, all of our great programs, and you hear from the GI Board of Governors and me on that one. And that's next Tuesday at 2 p.m. And then next Thursday at 2 p.m., we will be going over the revisions to NAVFAC DM 7.2, that great design manual that everybody uses. You'll want to check that one out. Diane Moog is from Portland State, is going to be our moderator. Mike McGuire from Lafayette College and Dan Vandenberg from Tennessee Tech, and potentially some NAVFAC staff are going to be on hand to answer some questions about that and walk you through the revisions, the first revisions to that manual in 39 years. So you can register for both of those and all of our upcoming events at our Eventbrite page. Guys, thank you so much for doing this today. I hope this was fun.
Thank you.
Yeah.
Hopefully.
And everybody go read that latest issue of GeoStrata, and we will see you with another live stream very soon.